Okay, well, thank you again for joining us. We're starting our module number 2 of our virtual power monitoring seminar series, and this module is going to focus on energy monitoring. And so we're going to start off, well, what are the building blocks of power? And it's going to be an introduction to AC power, but we're going to also mention a little bit about DC here. So first of all, what's the main differences between AC and DC? Many years ago, AC was chosen for us. AC can be a little bit complicated, but DC does exist in our kind of realm of power monitoring. Although most of the applications and loads and sources are AC, there are some DC applications, such as in DERs, okay, distributed energy resources. Well, when you have a string of solar panels, their links are in DC, so we can certainly measure that. You have batteries, and batteries maybe are battery strings in UPSs, which have been around for years. We've got a whole ton of customers. Most of our products are DC capable as long as AC, but they also measure not only the three-phase input and output of a UPS, but also that battery string and battery link, that DC link within the UPS, to kind of get a whole idea whether that UPS is working properly. And that is a DC measurement that can be done alongside AC in our products. Then you have a fairly new application, DER storage. You have these battery strings that go on now, lithium ion or other types of batteries and other types of storage, where, you know, when it gets on a cloudy day, you know, this is a way to store energy where your solar panels, your PV system isn't generating a lot. Well, you pull from the batteries that may be alongside that. Utilities are starting to use these, and other applications are starting to use these large scale storage systems, which of course are DC. We also have applications of high voltage DC links, which some utilities have been using. There's not one far from us connecting, was it Connecticut and I think Long Island, New York, maybe, I think, that we are actually monitoring with our Encore series of products. So really DC and AC, well, AC is the most common, but again, there are some DC applications within the type of power monitoring that we're talking about. Of course, DC is simpler. It's direct current. It's only one phase, so you're just monitoring a voltage and you're measuring the current of that feed or bus as well. But note that it may require special metering, and I say that because most of the power meters are assumed to be monitoring AC, and you have to check to make sure if they're not only DC capable, but if they're DC capable, and if you want to monitor current, that those CTs or current probes are also DC capable. An example of that may be a Hall effect CT. So most of the CTs out there, Rogowski coils, split cores, solid cores, those are AC only. So just as a little hint there, make sure you have the appropriate metering and the appropriate accessories and transducers if you intend to monitor DC. All right. Well, again, we focus on AC. Okay, AC, there's typically 3 phases that we measure, although there can be single phase, 2 phases, or we call split phase here in the United States. But typically we're talking about 3 phases, usually either 3-phase delta or 3-phase Y application. And just to get something out of the way here, a lot of people are still under the impression that you could just take one phase and multiply it by 3, and that's the total power. Well, really, that only works in a balanced system. And, you know, it's really not the usual, not the real world here. Maybe a load such as a motor or something may consume power in a balanced fashion when it's operating correctly, but that's not the real world, and certainly not the real power feeds. And the point is, and the takeaway, we need to monitor each phase and line individually, and the metering will handle adding that up for you properly to give you the total power in the system. So you need to monitor phase A, B, and C in a 3-phase system individually. Most capable tools are 3-phase tools, which you should be using, and they will do all this for you to give you accurate numbers. But do not take one phase and add them up or multiply them or whatever and make those assumptions. So again, we are talking about alternating current, and it introduces some complexities based upon the impedance of the loads, and that's called really the power factor, and the relationship between watts, VAs, and VARs are all tied together. And the power factor is the angle between the voltage and the current. And really, one way to put it, and one way we'll demonstrate it, I think, on the next slide, it's the difference in time from when they cross 0. So due to the impedance of the system, the power factor may change to be inductive, capacitive, or it may just be resistive, which is more along the lines in a DC circuit. There will be no power factor, okay, because it's not reliant on these issues. So as an example, a resistive power factor is the best you can get, which is a power factor of 1. It's the largest number you will see. And simply put, that can just be from a simple incandescent light bulb, not the new energy efficient lighting that we see out there like LED or the older CF bulbs. A heater, anything on a resistance coil, something like that, will give you a power factor of 1. We have inductive circuits, all right? Power factor of less than 1, which are, again, motors. Most power systems are inductive. So we'll have motors, transformers, things like that, and you will see a power factor of less than 1. But by convention, in our industry, inductive really implies a +1. So when you see +1, that's of course there, but when you do not see a sign here, it's implied to be inductive. That plus sign is implied there. Then you have the opposite of inductive, and it's capacitive power factor, which is -1. It's still less than 1, but you will see a minus sign here by convention. Okay, so it's the opposite. And where you may get a capacitive load in the real world, and something that's not on a bench or something like that, is power factor correction capacitors. They add in capacitance to improve the power factor, to make it more inductive, make it more closer to 1 rather, make it more resistive, I should say. But they're also compensation and mitigation devices. UPSs, modern versions of UPSs, have power factor compensation. And just note that sometimes when they're lightly loaded, and in other applications, they may actually provide a capacitive power factor. You may see that by the metering because it's kind of overcompensating because they're lightly loaded. So you may see that. So what's the relationship between them? So you can see here I have my voltage, and here I have my current. This is a resistive load. And what that means is that the voltage and current are in phase, and that's a power factor of 1. That's the best you can get. And you can see by their phasor diagrams, the voltage and the current line up on top of each other. Anything where there's a difference in this angle, and this would be inductive if we go negative here, or in the fourth quadrant here, I should say, and this would be positive if we go in the first quadrant. So anytime it's away from 1, you have either an inductive or a capacitive power factor. Well, inductive, the current lags the voltage, or it's out of phase, a power factor less than 1. And you can see here, if you look in time, this is where the voltage crosses 0, and you can see sometime later, this is where the current crosses 0. So you can see this in the phasor plot here. And the way to read these phasor plots, by convention in our industry, we have a counterclockwise phasor rotation. So it's going to point this way. It's going to rotate this way, rather. So to read this, kind of just leave the mouse cursor there, point your finger there, do whatever you're going to do. Rotate this graph counterclockwise. And you will see the voltage comes through that point first, and then the current comes through that point second. So that means the voltage is lagging the current by whatever period of time or whatever angle that is. And that angle represents what that power factor is. And we'll see that, I think, on the next slide. So the opposite situation is a capacitive load where the current leads the voltage. They're out of phase, a power factor of less than 1, but this is negative at this point. So if you look here, here's where the voltage crossed 0, but if this imaginary line, current crossed 0 before the voltage did. So if you read this counterclockwise spinning phasor, leave my mouse cursor there, and you can see that current is going to cross first, and then voltage will cross second. That you can see visually is a capacitive load. Okay, so that's the way to visualize the difference between the two. And of course, the metering will tell that for you. So this is the kind of the old power triangle that many of us saw in our basic circuits classes or other classes that we would have attended. Excuse me. And this is the angular relationship between watts, VA, and VARs. All right. And first, some basic math here. Power factor is the cosine of the angle between the voltage and the current. And if I go back a slide, it's the cosine of the difference of this angle right over here that we're talking about. All right. It can also be computed by watts over VAs. Watts is power. Okay. It's real power. VA is the active power, which is simply multiplying volts and amps together. So really, in theory, anytime you have an angle between the voltage and current, watts and VA will be different, and watts will be less than VA, which are the losses in that particular system. And you can see ideally the angle between voltage and current is 0. That means watts equals VA and the VARs equals 0. So, but you can see as that angle grows or the power factor increases, the VARs grow. All right. So the whole objective is to not have any VARs, and VA and watts are the same. And you can see there will be no angle. There won't be a triangle because this will just be a straight line here. So that's the theory behind this. Now, when we talk about power factor correction, matter of fact, we have a capacitor down the road here that switches in every morning that we see on our monitoring systems. The whole purpose of power factor correction, again, inductive loads are much more common than capacitive loads. So, most 99% of our loads out there in our systems are inductive. So what utilities do, what large facilities do, large plants do to save money on their utility bill, we'll talk about that a little bit later, is they introduce capacitance in the system, which increases the power factor closer to 1 or being resistive. So basically it adds negative VARs. So again, capacitive would have been in here. So if you put capacitance in there, you're going to reduce this VA and reduce this angle between watts and VA. So again, utility power factor correction capacitors increase the power factor towards 1 for more efficiency. So that works for them. It also works for you, but also in your plants or in your application, if you have a poor power factor, and if you're charged a power factor penalty by your utility, this may be something that you may want to consider to increase your power factor, either by power factor correction or other means, to reduce your energy bill and eliminate or reduce that power factor penalty that you may have. Okay, so we're going to go to our first poll here, and let's see if this works. We'll get it started here, and let me go launch it. And so question, what caused that power quality event that you saw there? All right, was it load switching? Was it utility outage? Or was it a power factor correction capacitor switching in? So we'll just give it a few seconds here for you folks to answer. And we've got 10 of you answered already. Okay, I can tell you a lot of you are wrong, but we'll get to that in a second. Okay, so we'll give you about 5 more seconds. Okay, let me end the poll here. Okay, we'll just share the results. Hopefully, can you guys see that? Okay, so the results are here. Let's see, 40% of you, 17 out of the 42 answered said load switching. One of you guys said utility outage, and 57% of you correctly said it's a power factor correction capacitor. So let me just let me close this out here. And Ken, can you still see the slides? Okay, we're good. I'm sorry. I can't see what we're presenting here. So the answer is it's a power factor correction capacitor switching in. So what happens oftentimes, depending upon the capacitor and how it's synchronized to the circuit, you will see a negative going oscillatory transient that occurs on your power system. And even though we're talking about energy monitoring today, a power factor correction capacitor is the device to improve the efficiency of the system and save money. You can see it does create a power quality problem potentially. And this is that transient that we're speaking about over here. Now, different systems can be susceptible to this transient. We've had factories shut down where PLCs cannot handle the transient. It gets rippled through and it locks up their computers and doesn't work right. We've had medical imaging, I should say, if I can speak right, that has been negatively affected by these power factor correction capacitors. So these are things that if you see these issues, you can contact your utility or build in mitigation so these transients will not affect you and your power systems. Okay, continuing along here, we'll progress and we'll talk about demand and energy, and we'll talk about what are they and kind of what are the differences and how they relate to each other. So there's demand. Usually measured in watts or kW. Probably that's kW more often, but again, it could anything. It could be microwatts, it could be gigawatts, megawatts, but typically we talk about kW. It's just based upon the multiplier. And what that is, what is demand? It's the amount of power over a certain time interval. And that's your demand interval, usually set by your utility. And that's typically 15 minutes, maybe 10 or 30 potentially. And the metering can be changed, but a lot of times you'll see that as a 15-minute demand interval. Now, energy, where demand is the amount of power over an interval, energy is an accumulation. So it's usually measured in kWh or watt hours. It would associate with your demand. So it could be gigawatt hours, it could be microwatt hours, megawatt hours. Typically, that's kWh, and it's amount of energy or power used over a 1 hour interval. Okay, so it's accumulation of power or consumption. So an example, 1 kW applied for 1 hour is 1 kilowatt hour. Half a kW applied for 2 hours, well, is also 1 kWh. Now, these are important because these are two different billing factors and measurement factors that you need to accommodate for in what you're doing. Okay, and really the difference between these is kind of like demand. If you use the old water hose analogy, demand is how much water is in the bucket that you fill with the hose, and energy is the rate of water flow, how fast that bucket is filling up. And both are very important to you, and of course the utilities where who are billing us. So let's start with a case study, and we'll talk about the Dranetz demand and energy, and we'll talk about the relationship between demand and energy. And before I do that, I just want to show you something. This is just live as of earlier today. If I can get this on, and I may have to just change tabs here. This is from our Dranetz software. Ken, you can see that? Okay, thank you. So this is live monitoring from our Dranetz software, and this is the demand curve over the last 7 days. So this is kind of a demonstration site we have at our factory in New Jersey, and we're looking at this main bus coming in from our utility, which is Public Service Electric and Gas, and we are looking at the demand curve of our facility. So we operate about 7, 8, 9 hours a day in our facility, maybe 10. People are working hard. So this is a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and Monday, Tuesday. You can see part of Wednesday, which is today. Okay, so what we're seeing is the power goes up in the morning as we start the day and goes down in the evening, and there's the evening, and it cycles, for this particular curve that we see. So I'm going to switch back to our PowerPoint presentation because it'll be just easier to show the relationship between demand and energy. And this is really what we saw over here before. And this is a 7-day demand curve, but also the relationship to energy being recorded at that same time. So you can see here is a Thursday, a Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, and part of a Thursday over here. You can see we start at about 7 or so, 6, 7 in the morning as our factory gets started. We peak around midday, 12 p.m., something like that. Our factory usually shuts down around 3:30 p.m. and the office staff goes home, 4, 5, 6 o'clock, depending upon when they start. And you can see this happens to be the evening, and you can see something turned on. This was in February, so maybe that was the heating system turning on. And you can see we're pretty consistent in the way we operate. And here's a weekend. You can see really no one came in over the weekend here. But if you look at the relationship between demand and energy, and you can see the energy is an accumulated plot. Okay, so we don't have negative energy unless we are producing power. So we are consuming power on a 24/7 basis here in our factory in New Jersey. And the best way to describe this, if you look at this weekend where we basically have flat utilization, our demand is flat, well, you can see our energy is flat as well, going up at a constant rate. Consider an airplane analogy where it's a constant glide slope, increasing altitude from whatever to the next altitude that it's supposed to go to. Then you can see our factory starts on Monday morning. Look at this little knee over here. We start accumulating energy at a higher rate because we're consuming more demand. Okay, we're more power in our facility. So it's kind of pressing on the gas a little bit harder. And then if you look more closely in the evening, over here, it flattens out again just to increase again. So that's the relationship between demand and energy. So of course, you want these to be as low as possible. You want your demand, you can see our demand floor, we want to make that lower, okay? And actually, if you would have noticed when I showed you the Dranetz data before, if I were to zoom that out, you can see our demand was reducing in our building over this year. We've done steps for energy efficiency, and you could see the baseline of our demand, this lowest demand that we had, was actually going down over time. Okay, that's the objective of an energy manager, is to say, okay, well, as an example, Dranetz in this example, you're down to 90 kW at your lowest on the weekend. What can you be doing to reduce that? Turn off lights, turn off machinery, do whatever you can do, because you're getting no production out of this and you're consuming a lot of power. So how can you improve that? Then the next steps are, well, how can you be more energy efficient? Change the lighting, change the drives, different things like that. So this is the relationship between demand and energy. In fact, you can glean a lot from demand and energy. To be quite candid, we have users and customers who can't give us details in government and military applications. And some of the spies, MI6 and CIA, actually use this information to get an idea what buildings and sites are doing. They can get an idea, you know, as an example, a whole bunch of computer servers moved in. You can look at the power signature and the demand. Let's say all of a sudden I'm monitoring a building, a whole bunch of boxes moved in and the demand goes way up. Okay, you look at the PQ wave shapes, it looks like electronic loads. So it looks like computer servers were put there. So that's kind of a hypothetical, but also a type of real application, and kind of looking at this application and looking at this information. So continuing along, we'll talk about utility billing. So example of some of the revenue metering standards, there's kind of two main standards bodies, excuse me, although, you know, different countries and different parts of the world have their own variations on this. So in the United States here, we have ANSI. I believe that's the American National Standards Institute, and it ANSI C12.1, C12.20. These are typically followed in the US, but of course other parts of the world can follow them as well. That's the code for electric metering, and it defines the types of meters, accuracies, reliability, performance calibration, and a whole bunch of things like that. And it's the compliance requirements for utilities and sub-metering, specifically when you're talking about billing. So when money's going to be associated to that, typically they need to be revenue certified meters. And that's typical around the world, you know, regardless of what metering standards you follow. And there is a certification process for that to verify that the meter is doing what it's supposed to do. So we move over to, in Europe, the IEC, the International Electrotechnical Commission for Europe and other parts of the world. They have their own versions, very similar, but they are a little bit different to the ANSI versions. And it's the same methodology to make sure that not only the meters are working right, the accuracies are right, the reliability and performance over the entire system is there. So we're not talking about just the meter itself, but any transducers that are used, CTs, possibly PTs, can work over the voltages, the currents, and the environmental considerations and temperature and humidity and things like that. So it's a little more complicated than just the meter itself. And some countries have localized versions of this. I know, like in Europe, there's the MID requirements. I'm not quite sure I recall what MID stands for, but other European countries take those MID standards and make their own versions of that. So it does get a little more complicated. So, but the application is typically for revenue metering, but not for spot checks or reference measurements. So typically when money is associated, you're going to bill someone or you are going to be billed. Well, then these kind of come into play. When it's used for reference, you do not have to have a certified meter. Usually certified meters are much more limited in their capabilities because they're usually fixed installed, and they're built and cost effective just for that voltage, just for that current, and specifically that wiring configuration where it's going to be installed. So what are the main differences between revenue certified and revenue accurate meters? So the overall objective of a revenue metering standard is to define the performance requirements of those meters so they can be accurate, repeatable, and give you reliable billing and other information. And both the ANSI, IEC, and other standards go well beyond the accuracy of the meter. As I said before, they go into the ranges of measurement, transducers, temperature, variations in power factor, and other aspects. So it does get quite complicated to get meters certified because there's a whole bunch more than the meter itself. So the takeaway here is even though a meter may not be revenue accurate or revenue certified, I should say, by a laboratory, it may have the accuracies of such a meter. Most of the Dranetz products fall into that. We have revenue accurate meters. They are just not certified for billing in the territories or regions. So they can be used in many applications that don't require certification, but do require measurements with similar accuracies. And those may be in check metering to verify that a utility meter is operating correctly. In fact, there are certain areas, I know the city of New York requires that there a certain percentage of the meters are random sampled to make sure that they are operating correctly, okay? Or from your own perspective, if you want to just put something in parallel with your utility meter to make sure that you're being billed properly. So, these are different applications, and of course, those within your facilities to monitor your own energy. So again, talking about utility billing, many factors go into a utility bill. As I mentioned before, you have demand charges and energy charges. Those are the most common and probably the largest portions of most of the utility bills. And we have a slide on that coming up as well. But we also have other things like power factor penalties. So you will get surcharge from your utility if your power factor exceeds a certain limit or goes below a certain limit, maybe 0.85, 0.7, 0.8, whatever it may be for from your utility. And this is where you may want to have some power factor improvement or power factor correction. We have some very funny case studies that we share during our seminars where the built-in power factor correction is offline in some of the facilities and they don't even know it. So you have ratcheting clauses in these contracts. And what that means is like a ratchet, like a tool, it can only turn one way, it can't turn the other way. Well, what that means is that when you exceed certain limits of your utility bill or contract, you start paying a surcharge and you don't stop paying that surcharge until that billing period or that contractual interval expires, and then it resets, and then you get to go pay the normal rate until you exceed that limit again. So you have to be careful. And you have fuel surcharges, and maybe there's more of that because the cost of energy and fuel is going up right now. You have stranded costs, and back years ago with the deregulation of a lot of utilities, this is their way of paying for their infrastructure that got stranded when they split up into delivery and supply companies, things like that. You also have delivery charges, and also in a modern world, energy provider versus distribution company charges. So simply put, you have the people who put the energy and the power on the wire. Then you have the company who the wire goes into your business or your home that you're buying the power from. You need to pay both. Sometimes they're different companies and there may be different bills from that. Today, you have another factor that goes into it with, from DERs and PV sites, wind sites, other alternative energy needs to be included in your utility billing with net summing and things like that. That even provides a whole other factor when we talk about the direction of power now and making sure that gets totalized and billed correctly. So again, some of the base things, you have demand charges, and again, demand is the average load over an interval, usually 15 minutes, but that can be 10 to 30 minutes. And you can see if you take 5 minutes on a 15-minute demand interval at 100 kW, another 5 at 400 kW, the last 5 at 1,000 kW, okay, you have an average of 500 kW. That is your demand over that demand interval. And then the utility would go and maybe bill you or charge you a particular charge based upon what that value is and what you've done historically. So when you talk about energy consumption, we're talking about usually in kWh, maybe large consumers would be in megawatt hours, who knows, but we'll speak about kWh, and it's typically a little bit smaller than demand charges, but regardless, consuming less energy, they all relate together. Demand and energy do relate together. It's just how fast you're accumulating it, and more importantly, when you're accumulating it. So many rate schedules have tiered rates that are time dependent. So it's a variable rate, not only based upon the tiers that you exceed. So in other words, the first number of kWh will be a particular cost per month. Then you go into the next tier of kWh, will be another cost per month, and so forth and so on. But then you also have time-dependent charges. These are time of use charges. And this is kind of what you may have heard the terms on-peak, off-peak, different types of rate schedules. And this is to encourage people and industry and homes to consume energy at off times where it's easier to supply and it's less strain on the utility system. So you think a hot summer day here in the northeast part of the United States, a lot of people have their chillers, their air conditioners running. It's a huge peak demand part. So they encourage people to do things on off times, maybe in the evening or during the day when people are at work, to run your dishwasher and stuff like that. So this is something where you may see an on peak, a partial peak, or an off-peak rate in your schedule. These are things that many years ago probably started for industry to make it more cost-effective for utilities to manage the loads in their systems and incentivize people in industry to use power at different times of day where there's less demand. But also with the advent of smart metering, and a lot of them started with in the United States with the Obama dollars 10 or 12 years ago, whenever that started, where now residential meters have the ability to measure when you're using power. So if you look at a traditional dial meter, well, that's just kind of a spinning dial. The utility can't tell when you use power during that day or during that month. They just do a reading probably every 30 days or every month, and they do the interval. But now with smart meters, just like in industry, they know exactly when you use the power. So they have the potential to charge you based upon the time of use on a residential perspective that they've been doing in industry for many, many years since electronic meters started to come out. So these are things, if you fall into this category, you may want to manage your utility bill a little bit better, whether we're talking about commercial or residential applications here. And of course, seasonal factors can come into play. Again, I mentioned the northeast part of the United States here gets very hot and humid during the summer, so is a big load on chillers and air conditioners. So the energy rates, the electric rates may go up during those periods of time. And you'll see similar things for your particular locations, wherever you may be. So that's really the basics of what we're talking about today. We're going to wrap this up with an energy savings case study. And this is part one of our two-part energy savings light bulb or lighting case study. And the second part will be in our next webinar. And I think I said that's on May 11th. Well, we're going to start here where what are the energy savings of these devices and how do we show that? And part two of this will be in our power quality section in our next webinar, and kind of looking, well, what are the effects of energy savings bulbs? What are the power quality concerns over that LED bulb or CF bulb that you just plugged into your house? Most likely it's a LED bulb, or you have an industry in your commercial aspect. So that we'll talk about at our next webinar in about 2 to 3 weeks. So we did a simple test here for energy savings lighting. We did a side-by-side energy comparison between a simple 60-watt incandescent bulb, a 14-watt compact fluorescent bulb that had the equivalent light output of a 60-watt bulb, incandescent bulb, and that same equivalent LED bulb, which was about rated at 9.5 watts with that same equivalent light output. So we're looking at the brightness of the bulb. These should provide the same amount of light output, but these are the different power usage or the watts associated with each particular bulb. So we put them side by side. We measured them with our products, and you can see the differences shown here in Dranetz. I apologize, it's a kW scaling on it. So, but we can divide that by 1,000. This is the 60-watt incandescent light bulb. As you can see, it was just about 60 watts, mostly a hair lower than that. The green plot here is the compact fluorescent bulb. They're still there. They're just not as common as LED is certainly today. But when we went to energy efficient lighting, certainly here in the United States, we had started with CF bulbs. They were much less expensive than the LEDs. So you can see we're about 12, 13 watts here. And the blue plot is the LED bulb, okay? A little less than 10, about 9.5 as its manufacturer claimed. Well, this plot here, this kind of really gives a good visualization on what's going on. Just ignore this stair step. That's just the plotting functions of our Dranetz software. Well, you can see this is the rate of energy accumulation of the incandescent bulb, that 60-watt bulb. So you can see how fast it's going up, like at a 45-degree angle here. Now you look comparatively to the what do we say, about 13, 14 watt CF bulb in green, and the 9.5 watt LED bulb. So really the bottom line is, would you rather be consuming energy at this rate or energy at these rates over here? So the takeaway is, definitely these devices do save the energy that they were claimed to do. They were spot on. It's not like we didn't believe them, but this is a very good demonstration of the concepts that we spoke about here before. And this is the very reason, certainly in the US, and I think other governments around the world, kind of put into law and insisted on people move to this energy efficient lighting. And but there are some questions regarding the power quality impacts of this, which we will not cover today. We will talk about at our next meeting on May 11th. So. Okay, so put that into real dollars, and you could see a 60-watt light bulb. Okay, it happened to be a Philips Duramax. These are just some details. The bulb cost was about 50 cents. You got to kind of ignore these numbers because things change a little bit, but oops. So the estimated annual cost to operate was $7.23. Okay, that's the Energy Star reading. So in the United States here, we have Energy Star, which is just a reference point. Okay, and basically it assumes that you're operating at 11 cents a kilowatt hour and 3 hours per day. It's just a benchmark here. And we have lighting and appliances are all rated based upon those assumptions. And it's to give the consumer an estimate of the cost of use over a year, an annual cost of that. Okay, and it's per day. So you can see this this just simple light bulb, old style light bulb. Its estimated annual usage is $7.23. based upon 11 cents per kilowatt hour, 3 hours a day times 365 days. So you can see where the cost savings here. Okay, that 14-watt compact fluorescent bulb. Okay, the cost is NA right now because they're almost not viable anymore. But to give you an idea, reducing from 60 watts to 14 watts, we're down to $1.69, which is basically taking this at 11 cents a kilowatt hour times three hours a day and 365 days a year. Even better with their 9.5 watt approximately LED bulb, which in this test cost $1.25. This was a couple years ago. I'm confident this is even less today. Well, the estimated annual cost is a little over $1. It's $1.14. So just by unscrewing that 60-watt incandescent bulb and screwing in that LED bulb, we're saving $6 or more a year just for that one light bulb. Well, times X number of light bulbs you have in your home, that translates into a large savings. And I know in my home, my family doesn't know how to turn off any lights, so I changed over to both compact fluorescent and then ultimately LED. I definitely saw the savings in my own home. So this translates to your residents, to industry, to commercial. So this is just talking about the basics on not only how to measure the power of these, but also how to do the math on it. And these are some important things when you talk about doing energy savings or mitigation aspects is, of course, well, what is it saving me? I did this change. I expected a particular reduction. Maybe a consultant came in and said, you're going to save 50%. Well, using monitoring tools such as those from Dranetz, you can easily measure the before. Here's what it is today. Then you go through with that retrofit and measure what it was after the retrofit to ensure that your expectations were equal to or maybe even better than what you thought they would be, and to confirm that installation did give you the value for your money and your time. But also, more importantly, as time goes on, well, does that continue to stay there? Do I have that continual cost savings? That's important to know as well, and to continually monitoring your energy, or to monitor your energy consumption, both on individual loads, your facility, and different parts of your facility. So again, the bottom line here, the math worked on these bulbs.